If we look again at the graphs that we saw in examples 3 and 4, we first had the graph of y equals x squared minus 4, and then the graph of y squared is equal to x plus 4. What we already established was that this second graph is not the graph of a function. So even though we can represent this we can represent this graph with an equation, we can't apply any function notation or any of the properties of functions to this equation. The equation that we had graphed in example 3, though, is a function. So the very first thing we could look at doing is applying function notation to this equation. So we can name this function, essentially, as f of x is equal to x squared minus 4. This function notation does a couple of things for us. The first one is that it gives us an easy way to refer to different functions. If we're dealing with more than one function, we could have f of x, g of x, and we can more quickly refer to specific equations. Another thing that it lets us do is identify points along our curve, or lets us look at evaluating our function at different points with a slightly different notation. For instance, if we consider the point here, which is 0, negative 4, we have a couple of different ways that we can indicate that value. We can use the xy pair, 0, negative 4. We could talk about evaluating the equation y equals x squared minus 4 at x equals 0. Or we could use function notation to say f of 0. When we use this function notation f of 0, what that means is we take our function f, and everywhere we have an x in that function, we substitute in a 0. So in our function here, we would substitute in 0 minus 4 to give us negative 4. In a sense, we have a more compact way of asking what would be a longer form question, and a quicker way of identifying different values. We could also look at that type of question in sort of a backwards manner. We could ask, where is f of x equal to 0? This means there are potentially points where our function value is equal to 0. We want to find the x values that would yield that. So if our function value is equal to 0, meaning our y coordinate is equal to 0, our points have to be somewhere along the x-axis. So what we would be looking for would be, in this case, these x-intercepts at x equals 2 and negative 2. So at f of 2, our function value is 0, and at f of negative 2, our function value is 0. So in answer to that question, it would be x equals 2 and negative 2. But again, in short, this function notation just means take the given function, or the referenced function, and evaluate it for whatever value is contained inside those parentheses, meaning we'll replace x with whatever that value is. We can look at doing this with some relatively simple statements like f of negative 7. This would mean we would take our given function, 3 times x squared, and then everywhere we have an x, substitute in negative 7, plus 2 times negative 7, plus 3 would be equal to 147 minus 14 plus 3, or 136. All we've done is essentially evaluate this equation for x equals negative 7, but now applying this approach of using function notation. We can also evaluate functions for a given expression. In this case, rather than plugging in a number for x, we're going to plug in negative x, which will give us 3 times negative x, that quantity squared, plus 2 times negative x, plus 3. Evaluating will give us 3x squared, since our exponent of 2 will cancel out that negative, minus 2x, so bringing that negative in our second term out front, plus 3. In part C, we're not looking to answer quite the same question we did in part A and B. Rather than plugging anything in for x, we're going to look at evaluating the opposite of our given function, which essentially just means putting a negative sign out in front of the entire expression. And then distributing that negative through to simplify. In part D, we have a slightly more complicated expression we're going to substitute in. But in essence, this is very similar to what we did in part B. Now we'll substitute in x plus h, that quantity squared, plus 2 times that quantity x plus h again, plus 3. And now we'll expand everything out and combine like terms. So expanding out 3 times x plus h squared would give us 3x squared plus 6xh plus h squared. Distributing the 2 through will give us 2x plus 2h plus 3. Again, in parts A, B, and C, or A, B, and D, all we're doing is evaluating that given function for a specific value, whether that's a number or some algebraic expression. And in part C, just sort of had a variation of that where we were finding the opposite of that given function. We could look at doing the same in example 6. In part A, we would evaluate our function for negative 3. Which would give us negative 6 over 9 plus 9, or 18, which would give us negative 1/3. In part B, we're going to plug in the opposite of x. So in the numerator, we would end up with negative 2x, and in the denominator, x squared, the square would cancel out that negative, so we would again just have x squared plus 9. In part C, we're asked to find the opposite of that given function. One thing to keep in mind is that multiplying by that negative would be the same thing as multiplying by negative 1. Or to take that even a little bit further, negative 1 over 1. Which means only the numerator will get multiplied by that negative to give us negative 2x over x squared plus 9. In this case, in parts B and C, we came up with the exact same result, even though we were evaluating two different expressions. That's not always true, but there are, obviously in this case, examples of where that would happen. In part D, then we're looking to evaluate this expression for x plus h, or to evaluate f of x plus h. Distributing through in the numerator would give us 2x plus 2h, and expanding out in the denominator would give us x squared plus 2xh plus h squared plus 9. Again, what we're doing is looking at simply evaluating this function notation for whatever expression or value is inside those parentheses. And just to clarify, a mistake that I probably should have caught here, is that in each of these cases, we should be referencing g of x. to indicate this named function g of x that we're considering in this particular example.